Welcome back to Calculus 1. I'm Dr. Jeff Grove. Today we're going to talk about the epsilon-delta definition for limits. We will have to have one more go at your comprehension of this topic. The basic idea: you want to prove that a function has a particular limit L. As x tends to a, the function doesn't even need to be defined at that spot, so I've put a hole in the graph here. The idea is if you choose some epsilon, I'm making it really big here, but epsilon is usually thought of as a small number. We'll have L plus epsilon and L minus epsilon as endpoints in the range. These correspond to points over here on the graph. The argument is there should exist some delta, more than one delta in all likelihood, so that if you go to a plus delta and a minus delta, delta units over on each side of a, excluding a itself, we're going to chop that out, then all of these other points will map into this epsilon neighborhood in the range. The idea being you can take epsilon to be as small as you'd like. If you can prove that there does exist such a delta that gets you to within that epsilon neighborhood in the range, then the limit is L. Closeness in the domain gets you close in the range to the limiting value L, as close as you need to that value in the range. Let's start with y equals f of x equals mx plus b, a generic line. Here we're going to assume that m is not 0. We're going to show that the limit as x goes to a of mx plus b is equal to m times a plus b. That should make a whole lot of sense if our theorems are true, since mx plus b is a polynomial, and polynomials are continuous. You may evaluate limits by simple substitution. But we're going to prove this using the epsilon-delta approach. So we're going to start with let epsilon greater than 0 be given. For straight lines, you always set delta to be epsilon divided by the magnitude of the slope. Suppose that we are within a punctured neighborhood of A, where delta is this epsilon over the absolute value of m. We can multiply through by the absolute value of m. And the absolute values can be combined so that we get epsilon is greater than the absolute value of mx minus ma. We're almost there. This is equal to the absolute value of mx plus b minus ma plus b. These would cancel. And here you have the function value, f of x, and here you have the proposed limit value. So provided you're to within delta units in the domain, you end up within epsilon units in the range of the limiting value L. That is the end of the proof. You should see one that's a little more interesting. We'll take the limit as x goes to 2 of the function x squared and prove that is equal to 4. So how do you go about this? How do you choose delta as a function of epsilon? That's always the goal on these limit proofs using epsilons and deltas. Given an arbitrary epsilon greater than 0, you have to find delta. The delta will depend upon the epsilon you choose. It will be a function of epsilon. So we're going to let epsilon greater than 0 be given. In order to reverse engineer this delta that we need, we're going to start off with where we want to go. We want the function value and the proposed limit value to be smaller than epsilon. And we'll try to break this apart and figure out how close we need to be in the domain in order to make that happen. Note that x squared minus 4 is a difference of squares, and we can factor that as x minus 2, x plus 2, both in absolute values. Now the absolute value of x minus 2 is the distance in the domain of the point x from 2. We want to have some statement about delta involving the absolute value of x minus 2, but we have this pesky little additional factor, the absolute value of x plus 2. Now, let's put an upper bound on our choice for this delta from the beginning. We're going to suppose that delta is no bigger than 1. What does that mean about our x values? That means you have x values that go between 3 and 1, no more than 1 unit in the domain away from the value 2. 1 unit this way, 1 unit that way from 2. What does that tell us about the absolute value of x plus 2? Well, x plus 2 is going to be bounded between 5 and 3, which means the absolute value of x plus 2 is also bounded between 5 and 3, because that's a range of positive values. In particular, the absolute value of x plus 2 will be less than 5. Let's see what the implications are here. The absolute value of x minus 2 times the absolute value of x plus 2 will be smaller than 5 times the absolute value of x minus 2. And we want that to be smaller than epsilon per our choice above. That means x minus 2 will be smaller than epsilon divided by 5. Now we know what we need to choose for our delta, as long as it's less than 1, to be the minimum of epsilon over 5 and 1, the smaller of those two, because we chose delta to be less than 1, but also we want delta to be epsilon over 5. Whichever one is smaller, that's the one that's going to work. It follows that whenever 0 is less than the absolute value of x minus 2 is less than this delta that we've chosen, because of this sequence of inequalities, that the absolute value of x squared minus 4 will be less than epsilon. And that's the end of the proof. Okay, So this was a fairly complicated one, and I won't give you one like this on an exam, but one like a straight line I might. So, at least, in my opinion, you needed to see an example like this. You needed to see the kind of play that we made with the epsilons and deltas. We call this epsilontics. There's a whole class that goes in depth into a study of this. It's called real analysis. That's in the upper division of a mathematics major. That's the course where we prove all those nice little theorems from calculus 1 through 3, and also try to extend those results to include as broad a class of hypotheses, as many functions, for instance, as possible. Let's do one more elementary example. Let's look at the same limit as in the last problem. The limit as x goes to 2 of x squared. If epsilon equals 1, find a suitable delta. So our function is a nice little parabola, and at 2 we should have a height of 4. I guess it's been drawn badly. We're going to choose epsilon equals 1, which means the y values go between a range of 3 and 5. How big, then, should we choose the delta? Well, let's track these numbers back to corresponding points in the domain. If 3 equals x squared and x is positive, we're talking about x equals the square root of 3, which is about 1.7. If 5 equals x squared, then x is equal to the square root of 5. The square root of 5 is about 2.23-ish. So you can see if this is about 1.7 and if this is about 2.23, we need to make our delta smaller than about 0.2. We're going from 1.7-ish to 2.2-ish. So if I set delta to be anything smaller, definitively smaller, .1 should do it. That will guarantee that if we stay within 0.1, that will track us back for sure within that little epsilon neighborhood in the range. Let's try that again, but we'll choose a smaller value for epsilon. So now we're choosing a neighborhood that goes from 3.9 to 4.1. Where do those track back in the domain, and how small does delta have to be now? So I need to solve the equations 3.9 equals x squared and 4.1 equals x squared. You can see x is going to be somewhere between the square root of 3.9 and the square root of 4.1. So I need good decimal approximations for those two numbers. My calculator is giving me 1.975-ish and 2.025-ish. It looks like we need to make delta something definitively smaller than the difference between these two numbers and 2. How about 0.02? That should do it.